What is sound? Sound is vibrating air. Sounds simple enough, but when we try to represent that visually, things can get a little confusing. You're probably used to seeing sound waves represented as wavy lines that resemble waves of water, but in reality sound waves are made up of areas of high and low air pressure. When we graph the pressure wave, we end up with the familiar waveforms that you see in audio software. Sound waves form from air particles colliding into each other. The body of air doesn't move, rather energy ripples through the air particles as they push into each other. If you look closely at your speaker while it's playing, you can see the diaphragm move back and forth to create the sound. The vibration of the diaphragm is what initially creates the alternating high and low air pressure that becomes sound. Your ear or microphone works in reverse from the speaker, where the air pressure moves the diaphragm of the mic and converts it into an audio signal. When you pluck a guitar string, the string makes a small amount of sound, but the vibrations from the string also vibrate the body of the guitar, which propagates sound waves in the same way the speaker diaphragm does. How are notes formed? A musical note happens when we vibrate the air particles at a consistent frequency. If the diaphragm of the speaker pulses 88 times in 1 second, it will produce a low A note, so the low A has a frequency of 55 Hz. We can produce this note digitally with a sine wave. A sine wave is the simplest kind of sound wave, as it only produces sound at the base frequency. If we look at the sine wave, we can see it fluctuates from low to high pressure at a consistent rate. This is what gives it that clean artificial sound. Looking at a sine wave in a spectral frequency display, and we can see that it only creates energy at one frequency. But what if we look at a square wave? A square wave is formed by layering harmonics on top of the bass note. Hypothetically, if we layered all of the harmonics up into infinity, we would end up with a perfectly square-shaped waveform. In reality, these harmonics cut off at the audible range, which is why you see small imperfections in the waveform. Looking back at the spectral frequency display, we can see that with the square wave that the bass note is accompanied by several harmonics that stack at regular intervals. Sound made in the real world tends to have this feature. When you pluck a note on a guitar string, the guitar vibrates producing the bass note as well as several harmonics. This is part of the reason why different instruments sound different when playing the same note. A sine wave is so simple it only has two discernible properties: frequency, which determines the pitch, and amplitude, which determines the volume of the sound. A note played on an instrument will also have a frequency and an amplitude, but will also have what's called a sound envelope, which is a way of describing how the musical note evolves over time. The sound envelope is made up of 4 parts: the attack, the decay, the sustain, and the release. The attack describes the time a wave goes from 0 amplitude to its maximum. Decay is the time between the maximum amplitude and its sustained level. The period where the wave has stabilized is the sustain. And the final drop from the sustain level to 0 is the release. These 4 properties are what give musical notes their unique timbre. What happens when sound waves interact? If you shine 2 lights across each other, neither beam is affected by the other because the light wave is the result of some kind of quantum magic. But sound waves are the result of air pressure, so they combine and merge when the 2 sounds are played in concert with each other. When we stack the harmonics on top of each other, we no longer see the original waves. They combine to form a new shape that represents the resulting sound. This phenomenon is known as phase interference, and it's why it's important to absorb the reflections in your room. Those reflections blend into the original sound, meaning that you're no longer hearing the audio as intended. The phase of a wave indicates how far evolved it is within a full cycle. If 2 waves have their crests and troughs aligned, then they're said to be in phase and the sounds will build off of each other and become stronger. If the waves are played so that their crests and troughs are inversely aligned, then they are said to be 180 degrees out of phase, and the wave cancels each other out. We almost always refer to sounds by their frequency, which is the number of times per second the wave completes a cycle. But no matter the frequency, sound waves always travel at the speed of sound. That means that for a high-frequency sound to fit more cycles into the same amount of time, the wavelengths have to get smaller, so the wavelength of sound is inversely related to its frequency. If a sound wave is played in a room with the same wavelength as the dimensions of that room, then the sound will reflect directly back onto itself and create a standing wave. You might have witnessed this effect playing around in the bathtub. If you create waves at regular intervals, you can get the waves to stack up and become extremely strong, with a very little amount of initial force. The wavelengths that correspond to your room's dimensions are referred to as your room modes. We have a whole other video on room modes if you'd like to learn more. The size of the waveform also dictates the thickness of the absorber we need to properly absorb it. The lower frequency sound with a large wavelength requires thick absorption to properly treat. By absorbing these sounds, we keep them from reflecting back onto the room and distorting the original sound we're trying to record or listen to. How can I tell what my room is doing to the sound? One of the most popular ways to test a room is by measuring the frequency response. This is a sample of your room that tells you which frequencies are reflecting back the strongest. A sound is played that sweeps through all the audible frequencies. The sweep is recorded, analyzed, and then graphed to give you a snapshot of the room's audio. A frequency response graph can look a lot like a waveform, but the two are meant to illustrate two separate audio concepts. With a waveform, the x-axis represents time, where with a frequency response graph, the x-axis corresponds to a frequency. A dip in a waveform is the negative pressure of the complete cycle, where a dip in a frequency response graph indicates a null or phase cancellation. Another useful way of looking at a frequency response is through a waterfall graph or histogram. These graphs give you an idea of the relative amplitude of a frequency, but also show you decay times, which can give you a better idea of what frequencies are lingering in the room. You can also get a good idea of your room's bass response by using filtered pink noise. Filtered pink noise is just a sample of all the audible bass frequencies. There's a sample of it on the GIK website if you need some. While playing filtered pink noise through your speakers, you can move around the room or listen with an SPL meter and measure and see where bass is building up in the room. If you're still trying to figure out how the sound is interacting with your room, visit gikacoustics.com where you can find tons of useful tools, articles, and videos, as well as our free advice form that was specifically designed to help you get details of your room over to our team of designers so that they can help you get the very best sound for your space. Get free acoustic advice. Visit gikacoustics.com for educational articles and tutorials.